Okay, so we're going to look at this. So I see over here they've declared L is equal to their side length. So they've defined the variable. Area equals A, they've declared the variable there, and volume equals V. Why does it make sense to choose L, A, and V instead of, say, X, Y, Z?
It's easier to remember, and when you look at the graph now, looking at what's X and what's Y, and it just matches the.
Yeah. It's easy to remember, right? And so you are empowered to declare whatever variables you want. Okay, it doesn't have to be X, doesn't have to be Y. Declare something that makes sense. When you see the V in the context of this problem, do you know that's representing volume? Are you going to get confused and think that's representing area? No, it's intuitive. Volume, V, so you declare it. So they've declared their variables, and then they've got some equations here. A is equal to the side length squared. Do you believe that? Are you convinced? Volume is equal to the side length cubed. Okay, let's go over here. They wrote it out in words very nicely. The area of a symmetrical cube. What does symmetrical mean?
It's all the same.
All the same. Now, are all cubes symmetrical?
Yes.
Yeah, okay. So that's kind of redundant, but it's clear, it clarifies, make sure we understand it. Would be the side length multiplied by itself. Does this verbal statement match up with this equation?
Yes.
Okay, good. The volume of a cube would be the sides cubed. How can we put a plus on this A? Go ahead.
Side lengths.
Side lengths cubed, right? It's not, we want to be very precise in our language. The side lengths cubed. So that's supposed to say lengths. Good. Up here they've got tables. Now let's see what we've got here. All right, is this column L? I'm sorry, let me ask this another. Is this column L squared as they have it labeled? Does this represent L squared? Be bold. Okay, you say no. Go ahead. Why? What should this column be?
No, it should just be L.
It should just be L, right? Just L. This column is just L. What should this column be?
L.
Just L. And let's see if these values make sense. When you plug in 1 and you multiply it by itself, you get 1.
Mm-hmm.
2 times 2 is?
4.
3 times 3 is? 9, and so forth. Let's go over here to the volume. We're going to cube. 2 times 2 times 2 is 8. 3 times 3 is? 3 times 3 is 27, and so forth on down the line. So those are looking good. Now let's come over here to the graph. What do you think about this graph? Wait, where did W come from? I'm a little confused.
We wrote it originally as length and width, and then we realized they're the same, so.
So you want to make this
L? It should be L.
Okay. What do you think about this graph, the volume graph?
I think it's true.
You think it's true?
Yeah.
Think it's a linear function if we were to graph this? Does
Yeah.
it look like a linear function to you? Anyone else? Go ahead.
It's exponential.
He says it's exponential. That's a bold declaration. Convince me.
The reason being is because it's squared and cubed. If you were to continuously put the same thing in, it's not the same distance. So like 1 to 4 there's a difference of 3, but 4 to 9 there's a difference of 5. So it's exponentially growing. It's not linearly.
So he says there's not a constant difference. If it's a linear function, there should be a constant difference, and there's not. So it's not linear. Okay, good. But he says it's exponential. It's not exponential either. But it's a good guess. If you were to graph these, if you were to go to Desmos and graph these, your volume function is going to look something like this. This will be your volume, and then your area function. This is L down here, this is A up here. Will look something like this. Okay, it'll look like a parabola. You can do that. Doesn't happen with a parabola. Okay.